Good evening, everyone. Welcome to Goscore Learning. I'm your Dhanya ma'am with your solution chapter, the second part. I'm the teacher of Department of Chemistry, Goscore Learning, the fastest growing edtech industry in the Middle East. Today, we are going to discuss about the first chapter, that is solutions. And in the first part of this video, in this particular chapter, we have already discussed about the different ways for expressing the concentration of solution as well as about the Henry's law. So today we are going to discuss about the Rawls law and ideal and non-ideal solution. That's a very important concept in this particular chapter. So are you all ready? Can we start? So before entering into the Rawls law, I would just like to give an introduction about the Henry's law, which we already discussed in the first part. That is, the Henry's law describes the quantitative relationship between the pressure and solubility of gas in a solvent. And we already know that the Henry's law states that the partial pressure of gas in vapor phase is directly proportional to the mole fraction of gas in the solution. So we can represent the Henry's law like the pressure is directly proportional to the mole fraction. So when we change the proportionality into equality, we will get P is equal to KH into chi, that is the mole fraction. Okay, so here the KH is what the Henry's law constant. Done. So in this section we have already showed a very important relationship between the Henry's law constant and solubility and temperature. That is, Henry's law constant is inversely proportional to solubility and it is directly proportional to temperature, right? That is, when the temperature increases, what happens? When the temperature increases, the KH value also increases. So, as the KH is inversely proportional to solubility, when the KH value increases, the solubility of gas decreases. So, what we can conclude? As the temperature increases, the solubility of gas decreases. That is the reason the aquatic animals are more comfortable in the cold water rather than in the hot water. Because in cold water, the temperature is decreasing. So, as the temperature decreases, what happens? The KH value of the gas decreases. So, as the KH decreases, the solubility of gas increases. That is why in the cold water, they will get more oxygen. So, they will be feeling more comfortable in cold water. But in hot water, the temperature increases, the KH value increases, the solubility decreases. That is why they are uncomfortable in the hot water. These all things we have discussed in the part 1 and about the applications of Henry's law, that also we discussed, isn't it? I hope you all are clear with that things. So today we are going to discuss about the solubility of liquids in liquid. Before that, I just want to give an idea about the vapor pressure of liquid solutions. Okay, the vapor pressure of liquid solution. Then you are already knowing about these things is from your lower grades itself, isn't it? The vapor pressure, what is the vapor pressure, everything, isn't it? So, we know that the vapor pressure is the maximum pressure exerted by a vapor in equilibrium with the liquid. So, here we want to know one more term, that is the volatile liquid. What do you mean by volatile liquid? The volatile liquids are those liquids that can form vapors. Okay? And non-volatile means they cannot form the vapors. So, for volatile liquids, there will be vapor pressure. They can exert the vapor pressure. But for non-volatile liquids, it cannot exert the vapor pressure. Okay? So, the vapor pressure depends only on the temperature and nature of the liquid, and it does not depends on the volume of the container or the amount of the liquid in it. Okay, and also see here, if we have a container, okay, we are filling a liquid in it. If this is the liquid in it, see, there will be definitely the particle on the surface, right? The particles will be there on the surface as well as in the bulk of the solution or the liquid, right? Particles will be on the bulk of the liquid. So, when you consider a particle in the bulk of the liquid, this one, see, this particle will experience the force of attraction from these four sides, right? From every side, it will be experiencing force. So, it will be more stable. So, the particles in the bulk of the solution, bulk of the liquid will be stable because it is experiencing force from all the sides, right? But at the same time, see, consider the particle on the surface. Okay, for this particle, it will be having pressure from force from these sides. On the top of the layer, there is no force experiencing, right? So, this particle is unstable or unbalanced. So, whenever it get energy, it can release from this surface layer and will be moving like this. So, whenever moving like this, it will be hitting the walls of the closed container. So, whenever it hit the walls of the container, definitely it will exert pressure, right? So, that is what we called the pressure exerted by the vapors of this volatile liquid. Okay. So, this is the concept about the volatile liquid. Now, let's see a solution containing liquid components. So, in the starting of this chapter, I told you here we are discussing about the binary solution. That means the solution which contain two components, right? So, for the binary solutions, here we are taking the first case where the solute is a liquid and solvent is also a liquid. Okay. Here we are taking the both the liquids are volatile. Okay. That means this two liquid solute as well as solvent can exert vapor pressure. Okay. So, see here. We can take the two liquids. Okay. So, in the first one, I'm taking the liquid A. Okay. We can consider this A as the solvent. Okay. And both the solvent and solute, they both are volatile. So, definitely they will produce the vapors, right? So, here I am filling the liquid A in the closed container at a constant temperature. Okay. So, this is the component A, right? That is the solvent. So, in a closed container, we are filling in the volatile solvent. So, definitely there will be some particles, the vapors will be formed, right? Okay. So, these vapors will exert a pressure. Okay. These vapors will exert a vapor pressure that is due to the pure solvent, because in this closed container, it contains only the liquid A, right? So, this liquid A exerts a vapor pressure that is due to the component A only. So, what we can say? It is the vapor pressure of pure component A, which we represent by PA naught. Okay? So, here PA naught is the pure vapor pressure. Sorry. PA naught is the pure vapor pressure of the component A. Okay. Same way, here I am taking the second component, that is B, which is the solute, right? The solute is also a volatile component, right? So, here we are taking the solute, liquid 1, liquid solute B. So, this liquid solute B, it contain only the B. Okay. So, this is also volatile. So definitely it will produce the vapors. See, these vapors will exert the pressure on the closed container at constant temperature, right? So what we can say that pressure, it is due to the pure solvent or pure component B only. So it will be the partial pressure due to the component B only, right? In the third case, see, we are taking again, sorry, here we are taking again a third container, closed container with the same temperature. Here what we are doing is we are mixing both this A and B together. So that is, these two are pure component. We are mixing this. So the third one will be a solution, right? So for here we are mixing A and B together. So what we can see there, see there will be few component as A. To that we are mixing the component B. Done. So for this case, what will be the pressure? Here there are both the component A as well as B. There we will apply the Rawls law. See, the Rawls law states that for a solution of volatile liquids, that is the two liquids we take here, the A and the B. So this is the solution of two liquid volatile substances. The partial pressure of each of the component of the solution, the partial pressure due to A as well as the partial pressure due to B, is proportional to its mole fraction present in the solution. So according to Rawls law, the pressure exerted by the component A in the solution is proportional to what? The mole fraction of that component A, right? Here, of course, there will be the vapors of B as well as the vapors of A. And according to Rawls law, the partial pressure caused by this solution containing the mixture of A and B, the partial pressure of each component is directly proportional to its mole fraction. So, here we can write partial pressure of component A is proportional to its mole fraction A, and also the partial pressure of component B is proportional to, it is proportional to the mole fraction of B, right? So, that is what the Rawls law states. Okay. So, here when you change the proportionality constant, we can write PA is equal to P naught A into chi A, right? Where P naught A is the vapor pressure of the pure component A, and PB we can write it as PB is equal to P naught B into chi B, right? Where P naught B is the vapor pressure of pure component B. Then this is what the Rawls law states. So the Rawls law is, it's very important one. So the Rawls law states that for a solution of volatile liquids, that means if the solute as well as the solvent is volatile liquids, the partial pressure, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. So I hope this is clear for you. Now let's see. We have got here what? We already got that when two volatile liquids are present in the solution, the pressure, vapor pressure of component A is equal to P naught A into chi A according to Rawls law, right? Say for component B, PB, it is equal to P naught B into chi B, right? So, According to Dalton's law of partial pressure, the total pressure, this is due to the pressure of individual component we got from the law, right? According to Dalton's law, the total vapor pressure, that is P total, okay, or the vapor pressure of the solution, we can represent it with S, okay. The vapor pressure, either you can use the P total or the vapor pressure of solution, both are right, okay. P solution, that is the total vapor pressure of the solution in the container, will be the sum of the partial pressures of the component of the solution. So, this is the partial pressures of the component. So, according to Dalton's law, the partial pressure of the solution is the sum of the partial pressure exerted by the components. So, how we can write? PS or P total is equal to what? P naught A into chi A plus P naught B into chi B, isn't it? So, here chi A, what is the mole fraction? Mole fraction is the mole fraction of A is number of moles of A divided by total number of moles, right? Here it is a binary solution. So, how we can write it? P naught A into chi A, I can write as Na divided by Na plus Nb, isn't it? That is what the mole fraction of A, number of moles of A divided by total number of moles. Okay, plus P naught B chi B divided by Nb plus Na, isn't it? So, here what we can write together? Total vapor pressure of the solution containing two volatile liquids, it will be P naught A into number of moles of A plus P naught B into number of moles of, sorry, this is number of moles, right? We have changed the chi B into, this is number of moles, right? We have rewrite the chi B into Nb by Na plus Nb, right? So, I can rewrite it as P naught A Na plus P naught B Nb whole divided by Na plus Nb. This is a very important equation. Okay. This is a very important equation that connect the Rolle's law and Dalton's law. Okay. And also one more thing. See, here we got it like this, right? PS is equal to pure vapor pressure of the pure component A into mole fraction of A plus vapor pressure due to the pure component B into mole fraction of B. Isn't it? So, we already know that what the vapor mole fraction of A plus mole fraction of B. If it is a binary solution, the mole fraction of the sum of the mole fraction of each component will be equal to 1, right? So, I can rearrange like this. This is PS is equal to what? P naught A. Sorry. I can rewrite it as P naught A into chi A. I can write it as what? Chi A is equal to what? 1 minus chi B. Isn't it? So, I am writing here instead of chi A, I am writing it as 1 minus chi B. 1 minus chi B plus what? P naught B into chi B, right? So, here what we will get? P naught A minus P naught A into chi B plus P naught B into chi B, right? This one I can rearrange like the P total. We are measuring the total pressure exerted by the solution or the total vapor pressure exerted by the solution, that is P total or PS. Both are right, okay? P naught A minus of chi B into sorry, yeah, plus P naught B into chi B into P naught B minus P naught A, right? So this is another equation that relates the total pressure. P total is equal to P naught A plus chi B into P naught B minus P naught A. Okay. So I hope this is clear for you. Now let's see one more thing. Here we have told that this is our container. We have mixed both the liquids there, right? We have mixed the liquid A and also the liquid B, right? So this is our solution. Okay. See here, definitely there will be some vapors. We are consider only the mole fraction of component in the solution, right? So definitely there will be some vapors that form on the top of the liquid solution, right? So here, see, here we have considered this. For this one component A, we have considered the mole fraction of A, and for second component we consider the mole fraction of B. This components is this one also forming the vapors there, right? So there also we will consider the mole fraction, that is here for the component A in the vapor phase of the solution. On the top of the solution, we will consider the mole fraction of component A in the vapor phase as Ya. This is the mole fraction of the component A in vapor phase, right? Same like there will be the component B also in the vapor phase. That mole fraction we will consider as YB, right? So now see, we know that what we got from the Rawls law, PA is equal to P naught A into chi A. Okay, this is from the Rawls law. Okay, for PB, it is equal to what? P naught B into chi B, right? We have already learned about the Dalton's law, which is applicable to gases, right? So according to Dalton's law, what we can write, the pressure of the component, vapor pressure of the component A is equal to total pressure into what? Total pressure into mole fraction of the component A. Okay. So either you can write here PT instead. We can write P of solution, the vapor pressure of the solution, right? So the vapor pressure due to component A is equal to total vapor pressure of the solution into the mole fraction of the component A in the vapor phase of solution. Okay. That is what according to Dalton's law, the partial vapor pressure exerted by the component A. Same like for the component B, we can write as PT or PS into YB. Right? Got it? So, here, this is very, very important relationship, that is, according to Dalton's law, the vapor pressure exerted by the component A is equal to total vapor pressure of the solution into mole fraction of the component A in vapor phase, and the partial pressure of the second component B is equal to total vapor pressure of the solution into mole fraction of the component B in vapor phase. Okay? So, see here, according to Rawls law, we got like this, right? According to Dalton's law, we got like this. So, we can equate this, right? So, when you equate this to, what you will get? PA is equal to what? PA is equal to, according to Rawls law, it is P naught A into chi A, and according to Dalton's law, it is PT, total pressure, into mole fraction of component A. It is not small letter A, it is capital letter A. We are considering the component, right? So, this will be A. Here also capital letter A. Because our solvent is A. We are denoting it with letter A, right? So, it is equal to total pressure into mole fraction of the component A in the vapor phase, not in the solution, in the vapor phase. Same like we can write for PB also, right? So here PB is equal to what? PB is equal to P naught B into chi B, which is equal to, according to Dalton's law, it is equal to Pt, that is the vapor pressure of the solution, into mole fraction of the component B in per phase, right? So, from these two equations, if I am writing, I am doing PA divided by PB, what I will get? PA is equal to P naught A into chi A divided by PB is equal to what? P naught B into chi B, right? Which is equal to total pressure PT into YA divided by PT into YB, right? So, I can rewrite it like this. These two terms will be getting cancelled. So, mole fraction of the component A in the vapor phase divided by mole fraction of component B in the vapor phase is equal to P naught A into chi A divided by P naught B into chi B. Okay, which I can rewrite like, what is chi A? Chi A is equal to Na by Na plus Nb, right? So this term will be P naught A into Na by Na plus Nb divided by P naught B into N chi B is Nb by Na plus Nb. So these two terms will be getting cancelled. So what I will get here? P naught A into Na divided by P naught B into NB, right? So, YA divided by YB is equal to P naught A NA divided by P naught AB NB. This is very, very important equation that you should know. Okay. Then we have to do some numericals based on this equation at the end of the session. Okay. So, here we have already discussed about the vapor pressure of a solution that contain two liquids. That two liquids are volatile in nature, right? And we have done we have discussed about the Rawls law that states that the partial pressure due to the component A is directly proportional to its mole fraction. And we have find out the representation of the Rawls law, and by comparing with the Dalton's law, we find out the total vapor pressure of the solution, right? The total vapor pressure of the solution is equal to vapor pressure exerted by the one component plus vapor pressure exerted by the second component, right? And also we have derived the equations that relates the vapor pressure of the component in the vapor phase with the partial pressure and the number of moles of the component, right? Now, we are going to discuss about the vapor pressure of solutions or solids in liquids. Okay. First, initially, we have discussed about the vapor pressure of liquids in liquids. Now, we are going to discuss about the vapor pressure of solution containing solids in liquids, right? So, solids in liquids. Here, in the initial case, what we took is both the solute and solvent are volatile. Here, the solvent is volatile, but the solute is non-volatile, right? So, I will note it down here. See, here we are taking the solvent A, that is volatile in nature, and we are taking the solute B, which is non-volatile, right? Okay. Now you say, see, here solvent A is volatile, right? So, what about the value of P naught A? This P naught A, of course, it's a volatile. It will exert the pressure, right? So, it will form the vapors that will definitely exert the pressure. That is the vapor pressure of the pure component A, right? So, this value will not be equal to 0 because there will be some pressure, right? But at the same time, for the solute B, see, here it is non-volatile. It will not form any vapors. So, is there any vapor pressure due to B? No, right? So, here the P naught B value will be equal to 0. Got it? So, now see, this is the closed container that we are maintaining at a constant temperature, right? Oh, here we have filled the liquid, that is, we took only the pure solvent A, which is volatile in nature. So definitely it will form some vapors, right? And these vapors will exert a pressure, that is what we called P naught A, the vapor pressure due to the pure component A, right? So this is our solvent A. Okay, now in the second container, see, in the second container, we are taking the same solvent, took the same solvent A, and to this we are adding some non-volatile solute, right? These are the non-volatile solutes that we added. Oh, now see, here for the pure solvent, see, the surface molecule, surface particles, sorry, here these surface particles are actually escaping from the surface and going into the vapor phase, and they exert pressure there, right? Here this much of surface is free for the solvent to form the vapors, isn't it? But when you add a non-volatile solute to the solvent, see what happens here. There are some spaces that is hindered by this solute particles, so that the number of vapors, the vapor formed will be lesser than compared to that of the pure solvent, because here the solute particles are hindering the formation of the vapors, right? Here you can see they are forming on the surfaces. They will hinder the formation of vapors from the solvent. So what actually happens here? Here the formed vapors will be lesser than that of the pure solvent. So for the vapor pressure exerted by the solution will always be lesser than that of the pure component, right? You understood how it is, why the partial pressure exerted by the solution containing a non-volatile solute is lesser than that of a pure solvent. Okay. So, here what we can write, the total pressure in this solution. Okay. The total pressure of the solution containing the non-volatile solute and volatile solvent. What we can write? This is equal to PS. The vapor pressure of the solution is equal to the pressure exerted by the component A plus partial pressure exerted by the component B, right? Here PA is equal to, according to Raoult's law, it is equal to P naught A into chi A, and PB is equal to P naught B into chi B, right? So total pressure of the solution is equal to P naught A into chi A plus, what is P naught B? P naught B is 0, right? So this term will be 0. So we can say that the partial pressure of the solution is equal to P naught A into chi A, right? This is the partial vapor pressure exerted by the solution. Okay, and this is the vapor pressure of the pure solvent, PA. Okay, so see here, initially when you take the pure solvent, the vapor pressure P naught A value is more. But in the solution, its vapor pressure, it's getting reduced. It's lowered because of the solute particle hinders the formation of the vapors, right? So there we can say there is a lowering of vapor pressure, isn't it? This value is higher. There what the vapor pressure we are getting is lower value. So we can say there is a lowering of vapor pressure. Understood? So now let's see. The next term is the ideal solution and the non-ideal solution. I hope the Rawls law, Dalton's law, and how this are related, all these things are clear for you. In the last slide, we have discussed about the solutions that contain liquid component as well as the solid and liquid component. Now we are going to discuss about the ideal solution. What do you mean by an ideal solution? If a solution that obeys the Raoult's law, that is, if the vapor pressure of the solution is equal to the sum of the vapor pressure of each component, we can say that that solution is an ideal solution. Or in simpler words, we can say the solutions which obey the Raoult's law is what we call the ideal solutions. See, ideal solutions, the solutions which obey the Raoult's law over the entire range of concentrations are known as ideal solutions. Okay. So for an ideal solution, what we can say here, the total pressure of the total vapor pressure of the solution is equal to sum of vapor pressure of component A plus vapor pressure of the component B. Okay. So here I have given some examples for the ideal solutions, that is N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene are few examples for ideal solution. Usually the solution will, none of the solution usually show this ideal characteristics, ideal solution behavior. Usually upon very dilute solutions, upon diluting the solution only, they show this ideal character. Okay. So I think this is clear. Ideal solution, that solutions which obey the Raoult's law is what we call the ideal solution. Now let's see what is the thermodynamic conditions for an ideal solution. When we can say a solution is ideal in terms of the thermodynamic conditions. So imagine if we are taking a solvent A and a solute B. So when you mix this together, the solution is forming there, right? See, I can write it like this. See, this is your solvent A. Okay, this is the solvent A, and there will be interaction between the solvent molecule, right? And this is the solute particle, that is B, right? So there also between this B, there will be an interaction between them. So when you mix these two together, what you will get? You will get the solution, right? This is your solution. See, here there is an interaction between the solvent particle interaction between the solute particle, and when they mix together, there will be interaction between the solute and solvent particle that lead to the formation of solutions, right? So, for an ideal solutions, if this interaction between the solute and solute, solvent and solvent is equal to the interaction between the solute and solvent is, then it will show the ideal characteristics. Then it will behave as an ideal solution. Got it? See, if the molecular interaction before and after mixing, that is the interaction before mixing, the interaction between the solvent and the interaction between the solute is equal to the interaction between the solute and solvent after mixing is, then the solution will be an ideal solution. So for an ideal solution, what we can say, AA interaction is equal to BP interaction, which is equal to AB interaction. Then only the solution will be an ideal solution. Understood? So also see here, we know that whenever there is breaking of bonds, then energy is utilized. Energy is required there, right? Whenever new bonds are forming, their energy is releasing, right? So here, when you are mixing the solvent and solute together and the solution is forming, then what actually happens? This bond between this solvent is breaking and between the solute is also breaking, and a new bond is formed in between the solvent and the solute, right? See, when the energy absorbed for the breaking of the solvent-solvent and the solute-solute interaction is equal to the energy that is released during the formation of this solute-solvent interaction. Okay, so for an ideal solution, what we can say, the energy that required to break this bond and this bond will be equal to the energy that is released during the formation of a new bond in between the solute and the solvent. See, if here I am requiring 2 joules of energy, here also I am requiring 2 joules of energy. So for an ideal solution, the energy released when this two solute and solvent joined and a new bond is formed in between them will be 4 joule. So here the enthalpy change will be 4 minus 4, that is 0. That is what the second point. Here for an ideal solution, delta H mixing will be 0. That is the energy absorbed when solvent-solvent bond and solute-solute bond are broken is exactly equal to the energy released when the solute-solvent bond is formed there. Because here the solvent-solvent interaction, solute-solute interaction and solvent-solute interaction are same. So the energy required to break this bond and this bond will be equal to the energy released during the formation of a new bond between the solute and the solvent, this bond formation. Understood? So this is the second condition. And the third one is, for an ideal solution, if you are taking this AA plus BB leading to the formation of solution to AB. Here if you are taking 2 liters of A and 2 liters of B, the interaction between AA, BB is equal to that of AB, right? So here the product formed will be what? It will be 4 liter, right? So what about the change in the volume? It is 4 minus 4, that is equal to 0. So for an ideal solution, the intermolecular attraction is not changing. That is why the interaction between AA, BB is equal to AB. After the mixing, the volume remains the same, right? So here the delta V of mixing will be 0. And the last thermodynamic condition is delta S mixing. That is the entropy. Okay, entropy is the measure of the randomness. Here we are taking A, here we are taking the solute B. When you mix this together in that particular solution, A and B will be there. So definitely there will be measure of randomness. So this measure of randomness value will be positive value, right? Entropy is a measure of randomness. So in solution, there are two different type of particles, A and B. So this are present in the entropy of the solution will always be higher than the pure solvent because there is randomness is there, right? So definitely the entropy of mixing will be a positive value for an ideal solution. These are the four thermodynamic conditions that is required for an ideal solution. That is the intermolecular interaction between the solute and solvent will be equal to that of the solute and solvent. Second one is delta H of mixing. The enthalpy of mixing will be zero because the energy required to break the bond between the solvent and between the solute will be equal to the energy released when a new bond is formed in between the solute and solvent. So there delta H mixing will be 0, and also since the interactions are of equal, the volume, there is no change in the volume after mixing. The volume before and after mixing will be equal. So delta V mixing, change in the volume, that is the final volume minus initial volume, that is initial volume is 4, final volume is 4. So the change in the volume will be 0, right? Also the entropy will be a positive value. These are the four thermodynamic conditions that are required for the ideal solutions. I hope it is clear for you. Now we are going to discuss about the non-ideal solutions. Okay, and before that, we want to draw a graph of ideal solutions. Okay, see, for an ideal solutions, we are going to draw the graph. We are plotting the vapor pressure, here we are plotting the vapor pressure, and here we will be taking the mole fraction. Okay, here we will be taking the mole fraction, right? Here we have two components, right? We have the component A and the component B. So the mole fraction of A is chi A and the mole fraction of the second component is chi B. So here I am taking the mole fraction of A as 0. Here it is the maximum value, that is equal to 1. So its mole fraction is increasing from left to right. Okay. For the second component, I am taking the mole fraction chi B is equal to 0 and its value is increasing from right to left. It will be demonstrating like this. Chi B is equal to 1 here. Okay. See, according to Rawls law, what we learned? PA is equal to what? P naught A into chi A, right? Whenever this chi A value is 0, there is no pressure. So it will be 0. For the first component, it will be 0 since the vapor pressure is directly proportional to mole fraction. As the mole fraction increases, the pressure also increases. So we will be getting a straight line, right? So when the mole fraction is equal to 1, what we will get? PA is equal to P naught A. So when the mole fraction is 1, the vapor pressure exerted by the component A is equal to the vapor pressure of the pure component, right? So here for this graph, I am taking the first component, that A is more volatile. Okay, the condition is here we are taking the component A is more volatile than component B. So if component A is more volatile means its vapor pressure due to the pure component A will be higher than that of the B, right? So what I can write here? So what I can write here? It is P naught A is greater than P naught B, right? Why? Because the A is more volatile. So it will produce more vapors. So of course the vapor pressure of the component A will be greater than that of the component B, right? So here this is the mole fraction of A is 0 and this is the point where the mole fraction of A reaches the maximum value, right? So, according to Rolle's law, since it is directly proportional, we can draw like this, right? So, we can draw it like this, right? The line will be coming from here and it will be, since it is the first component which is more volatile, here for the value chi A is equal to 1, what I will get? This will be what? P naught A, right? Because here the chi A value reaches the maximum, right? So this will be the P naught A. Same way, P naught B. How we will find out? Because here from here the lowest value 0. There the pressure due to component B is 0. And I am drawing a graph like this. But this is a straight line. It's not coming well. See, straight line coming, and this will be here chi B is 1, right? So this value will be P naught B, right? So here one point, this PA and P naught A and P naught B curve is coinciding where pressure due to component A is equal to that of B, right? And when you joined these two lines, these 2 points, when you joined, you will be getting a straight line. We will be getting a straight line. This line gives the vapor pressure of the solution. That is PS equal to PA plus PB. Right? This is the graph that represents the vapor pressure and mole fraction of an ideal solution. Okay. Now let's see the non-ideal solution. The non-ideal solutions means those solutions which do not obey the Rolle's law. Okay. So, according to Rolle's law, what we learned? P of total vapor pressure is equal to P naught A. Sorry. The total vapor pressure is equal to PA plus PB. Right. So, if the total pressure is greater than or lesser than the pressure of the individual component, that's what we call, that type of solutions are what we call non-ideal solutions, right? So when a solution that does not obey the Rolle's law over the entire range of the concentration, then that type of solutions are what we call the non-ideal solutions. Understood? So the vapor pressure of such solutions, that is the total vapor pressure of the solution, is either higher or lower than the vapor pressure of the individual component. That is the sum that we described by the Rolle's law. Okay. So, if this total vapor pressure of the solution is higher than the sum of the individual component, that is what we called positive deviation from Rolle's law. And if it is lower, then it is called negative deviation. See, if the vapor pressure of the solution is higher, the solution exhibit a positive deviation, and if the total vapor pressure is lesser value, lower value, then it exerts a negative deviation from the Rolle's law. Okay. Now see the conditions that are required for positive deviation as well as for the negative deviation. For positive deviation, there, what we told here, for the positive deviation, the total pressure will be greater than that of the PA plus PB, right? So, what actually it indicates here, the total pressure is greater. That means the solute-solvent interaction is very weaker, right? So, there the interaction, the solute-solvent interaction after mixing is decreasing. That is why the vapor pressure of the solution is increasing, right? If the solute and solvent have more interaction, there won't be too much of vapors producing. The vapor pressure of the solution will be lower value. Here, the vapor pressure is higher value because the solute and solvent interaction is very weak. So, whenever the solute-solvent interaction after mixing is decreasing, more molecules moves into the vapor phase, contributing more pressure in the solution. So, Here, the total vapor pressure of the solution is greater than that of the pressure of A plus PV, right? So here, the delta H mixing will be a positive value because here after mixing, there will be a weak interaction between the solute and solvent. So there, the bond formed is very weaker. The energy released will be lesser value. So the delta H mixing value will be a positive, and also the delta V mixing will be positive value. And here are some examples for the positive deviation, that is acetone and hexane mixture, alcohol and cyclohexane mixture, water and alcohol mixture. These are the examples for the solutions that show positive deviation from the Rawls law. Okay. Now let's see the negative deviation. The negative deviation means the solute solvent interaction after mixing is stronger. There the vapor pressure due to the solution is lesser than that of the solute and the solvent. So here the total vapor pressure will be lesser, right? Will be lesser than that of PA plus P. Okay, why? Because there the solute and solvent interaction after mixing is greater. So there won't be formation of too much of vapors in the solution. So definitely the vapor pressure will be decreasing. So the vapor pressure of the solvent solute interaction is lesser than that of the solute plus solvent. Here the delta H mixing is negative and delta V mixing will be a negative value, and the examples are, if you are adding any volatile strong electrolyte is dissolved in water, it usually shows a negative deviation. And also the phenol and aniline mixture, acetone and chloroform mixture, water and nitric acid mixture, water and HCl, all this shows a negative deviation from the Rawls law. So the ideal solution, non-ideal solution, positive deviation, negative deviation, along with its example, it is very important. I hope it is clear for you, right? Now, see, this is what the graph that we draw for the ideal solution. So, whenever there is a positive deviation, there will be an increase. So, for the positive deviation, the graph will be like this, isn't it? That is, the pressure is increasing there for positive deviation, and for negative deviation, it will be down below the straight line. Okay. Now, I hope this all concepts are clear. Now we can do some numericals that based on the topics that we covered till now. Okay. So, first one is, at 25 degrees Celsius, the vapor pressure of pure liquid A having the molecular weight 40 is 100 torr, while that of the pure liquid B is with molecular weight 80 is 40 torr. Calculate the vapor pressure at 25 degrees Celsius of solution containing 20 gram of each. Okay. Now see, what are the things given that we can take it out? So, the vapor pressure of the pure liquid A. Vapor pressure of pure liquid A means what it is given there? P naught A. That is the vapor pressure of the pure liquid A, right? P naught A is given as what? 100 torr, right? And also the vapor molecular weight of A is given, that is the molecular weight of A, component A, it is given as what? It is 40, right? And for the B, component B, what it is given? P naught B, it is given as P naught B is equal to 40 torr, right? 40 torr, and the molecular mass of second component, it is given as 80, right? So, what we want to find out? Calculate the vapor pressure of the solution that contain 20 gram of each of the component. Then what is the weight of the component? Each component, it is 20 gram, right? Weight is equal to 20 gram, and you want to find out the vapor pressure of the solution. Okay, this is what you want to find out. How we will find out? This is simple. By substituting the values only, we will get the answer, right? So from here, the weight and the molecular mass is given. From that, we can calculate the number of moles of the component A, that is mass by molar mass, that is equal to 1 by 2, right? And for P naught, the second component B, the mass and molar mass is given. So the number of moles of B, it is equal to mass 20 divided by molar mass. It is equal to 1 by 4, right? For the component A, what is the chi A value? It is number of moles of A, 1 by 2 divided by number of moles of A plus number of moles of B, right? 1 by 2 plus 1 by 4. So what we will get here? 1 by 2 whole divided by 4, 4 plus 2, 6 by 8. That is, we can write as 3 by 4, right? So when you multiply, you will get 1 by 2 into 4 by 3. That is 2 by 3 is the mole fraction of the component A. Okay. So for the second component NB, what we will get? How we will find out the chi B? Same like that of chi A. We can find out chi B is equal to 1 by 4 divided by chi A plus chi B. We get it as 6 by 8, right? So when you do it, what you will get? Same. What we will get here? This will be equal to 1 by 4 into 8 by 6. That is 2 by 6, right? Here we're getting it as 2 by 6. Okay. So when substituting the values, P total according to Dalton's law, it is equal to PA plus PB, that is equal to what? PA is equal to P naught A into chi A plus P naught B into chi B, right? So what is P naught A? It is given as 100 into chi A value. We got it as 2 by 3 plus P naught B is given as 40 into chi B value. We got it as 2 by 6, right? So after doing this calculation, we will be getting the total vapor pressure exerted by the solution, right? So once after doing the calculation, 200 by 3, or else we can do one thing, we can simply take this. See, here we can simply take, without taking the mole fraction, we can give the values of the Na by Nb. Okay. Into Na, what we got? It is 1 by 2 whole divided by Nb. Sorry, Na plus Nb, we got it as 6 by 8, right? Divided by into Nb, we got as 1 by 4 divided by Na plus Nb, we got as 8 by 6. 6 by 8, right? So by doing the calculation, we can find out the sum of the vapor pressure or the vapor pressure exerted by the solution. Now we can move on to the next question, that is, a mixture of ethyl alcohol and propyl alcohol has a vapor pressure of 290 mm and at 300 Kelvin. The vapor pressure of propyl alcohol is 200 mm. If the mole fraction of ethyl alcohol is 0.6, its vapor pressure in mm at the same temperature will be. So how we will find out? What it is given here in the question? See, a mixture of ethyl alcohol and propyl alcohol has a vapor pressure. So we have provided with the vapor pressure of the solution, that is 290 mm. Okay. At a 300 Kelvin, the vapor pressure of propyl alcohol, it is given P propyl alcohol, it is given as what? 200 mm. if the mole fraction of ethyl alcohol is 0.6, would you want to find out what will be the mole fraction, vapor pressure at the same temperature? We want to find out the vapor pressure of ethyl alcohol. So how we will do? Here, once we get the number of moles of E, we can find out the number of moles of propyl alcohol, right? That is 1 minus 0.6, isn't it? That value will be 0.4, right? So here we have the values of total solution, pressure of propyl alcohol, and the pressure of the ethyl alcohol. So here what we want to find out is the partial pressure exerted by the ethyl alcohol. Just see the equations. I'll be back. Okay, so by doing the PS is equal to what? The pressure of propyl alcohol plus pressure of ethyl alcohol, right? So this will be what it is. PS is equal to the total vapor pressure. See, P naught SPP plus PP it is given. See, total pressure it is given 290 plus the pressure of this one it is given 200 plus this is what we want to find out, right? Sorry, there was some mistake. Let me check it. Just a moment. See, here we took it as wrongly because the vapor pressure of propyl alcohol is given here, right? It is not the vapor pressure of propyl alcohol. That is the vapor pressure of the pure component, propyl alcohol, P naught B. And we want to find out the vapor pressure of the ethyl alcohol in its pure state, right? P naught E. So here what we will get? See, here we will get Pp is equal to P naught P into number of moles of P divided by Np plus Ne plus P naught E into number of moles of E divided by Np plus Ne, right? So, what we can write here? PS value, it is provided in the question. It is 290, which is equal to P naught P. It is given 200 into Np. That is what given as 0.4. This Np plus N1, it is 0.6 plus 0.4. That is 1 plus what? P naught E. P naught E that we want to find out. P naught E into number of moles of E. It is given 0.6, right? So, by doing this calculation, that is 290 is equal to 200 into 0.4. It will be 80 plus P naught E into 0.6, right? So, by dividing this one, 210 we will be getting 210 divided by 0.6 will be the P naught E value. Okay. So, after doing this, we'll be getting that is 2100 divided by 6. By doing this, we'll be getting the value 350 there, right? So, the partial pressure of the pure component ethyl alcohol will be 350. So, the option B will be your answer. Okay. So, now we can move on to the next question. That is, two liquids A and B have the vapor pressure in ratio 2:3. So, the pure vapor pressure of the pure component A is to B, it is given as 2:3. So, pure component A, it is 2, and for the second component B, it is given as 3 at certain temperature. And A and B forms an ideal solution. That means it follows the Raoult's law. And the ratio of mole fraction of A and B in the vapor phase, that is YA is to YB. See, the ratio of mole fraction of A and B in the vapor phase it is given. That is YA and YB it is given. YA is equal to 1 and YB it is equal to 3. Then what is the mole fraction of A in the solution at the same temperature? That is what you want to find out. What is the mole fraction of A in the given solution? So how we will find it out? See what we learned from the equation. See here. See here what we learned, YA by YB is equal to P naught A NA by P naught B NB, right? So substitute that equation, simply you will get the answer. Okay. See YA by YB is equal to P naught A NA by P naught B NB, right? So here YA and YB value it is given. So it is 1 by 3 is equal to P naught A, it is 2 into number of moles of A that we want to find out, and P naught B it is 3, and instead of NB what I can write, it is equal to 1 minus NA, right? NA by NB will be there. If you are writing the mole fraction, if you are writing the mole fraction here, that is what we done here, right? See, chi A by chi B we took and we cancelled the term. So, here I can write it as 1 minus Na. By substituting these values, we can find out the mole fraction of A. Or instead of that, I can take the mole fraction of A itself. Sorry, it is not the number of moles. We want to find out the mole fraction, right? It is the mole fraction. Chi A we want to find out. So, it will be what we can write here. It is, so not N, it is chi, right? Chi A and chi B. So here I can write chi A 1 minus chi A, right? Chi B, I can rewrite it as 1 minus chi A. So after doing this, 3 into 1 minus chi A is equal to 6 chi A. So 3 minus 3 chi A is equal to 6 chi A. I will get the value as 3 is equal to 6 plus 3, 9 chi A. That is 1 by 3 is the mole fraction of component A. Right? So, this is the questions. So, if you are asking the question, it is given the mole fraction of A and B in the vapor phase. That's why we took the YA and YB, and the vapor pressure of the pure component A and B, it is given as 2:3. And what we want to find out, it is not number of moles. I took it wrongly as number of moles. It is mole fraction of A we want to find out, right? That is the chi A value. Okay. This is given the mole fraction of A that we want to find out. So, it is chi A. So, when you substitute the equation, what we can write there? Chi A by chi B. The chi B, we can rewrite it as 1 minus chi A. Okay. So, I hope it is clear. I made a little bit mistake in that. I hope that portion is clear for you. Okay. Now, the next question is the vapor pressure of A and B at 25 degrees Celsius are 90 mmHg and 15 mmHg respectively. That is the vapor pressure of the pure component A. P naught A, it is given as 90 mmHg, and P naught B, it is given as what? 50 mmHg. Okay, I am not putting the unit. 15 mmHg. Okay, if A and B are mixed in such that the mole fraction of A in the mixture is 0.6. Okay. So the mole fraction of A in the mixture, it is given as chi A as 0.6. Okay. If chi A is 0.6, what is the value of chi B? It is 1 minus 0.6, that is 0.4. Then the mole fraction of B in the vapor phase is, that is YB it is given. Okay. YB, the mole fraction of B in the vapor phase, it is given as X into 10 raised to minus 1. Then you want to find out what is the value of this X. Okay. See how we will find out the value of this X, that is the mole fraction of component B in the vapor phase, right? So for that, what we want to find out initially, first you have to find out the total solution, vapor pressure of the solution, that is equal to P naught A into chi A plus P naught B into chi B, right? So here P naught A, P naught B, PA and chi B value it is given. So by simply substituting, you will get the total pressure, vapor pressure of the solution. So once you get this value, how you will find out this? Because we know that according to Dalton's law, PS is equal to total pressure. P is equal to P of component A is equal to total pressure into mole fraction of component A in the vapor phase, right? Mole fraction of component A in the vapor phase. Same way, pressure due to B is equal to what? P total into mole fraction of component B. PB we can find out it is P naught B into chi B, right? And the total pressure we find out here. Based on that, we can find out the YB value and then we can substitute the X. Thereby, we can find out and once we get the YB value, we can rewrite it in the terms of X into 10 raised to minus 1 and we can find out X value. I hope this is a easy one. You will solve it out by your own. Okay. So, this is about the ideal equation, ideal solutions, non-ideal solutions. Okay. I hope this session is clear for you all. And I will be coming with the second part in third part of the solution chapter, which will include the colligative properties and abnormal masses. Okay. Meanwhile, go through the portions that we discussed till now. If you have any doubts, you can put in the comment box regarding it. And one more thing, your Satin sir will be coming on live on the 1st November 2023, that is on the Wednesday, with a new chapter, integrals. The first part of that integrals chapter. So stay tuned with us. Thank you for your time.